Okay, good morning everybody and welcome to this special dissertation in a very special time and in a very special format. It's a bit strange for us to be in this kind of situation with not that many participants here locally, but we are very happy to see that we're having lots of people online instead. So, this is a very big day for Muhammad Abu Bakar, who will present his thesis today. We have been working a long time together here at Sweden University. I've been involved in all of his research. And all the way from the master thesis time up to this final day. So together with us we have four prominent persons who will be reviewing Muhammad Abu Bakar's thesis work. So first of all is the opponent, Associate Professor Jorge Garcia from University of Oviedo in Spain.
So, nice to be here. Thanks very much for the invitation.
Yeah, welcome. Then we have Professor Torbjörn Thiringer from Chalmers University of Technology. Then we have Professor Bängsson from Lund University. And yeah. And
hi from Torbjörn, now that you have unmuted me.
Yeah. Oh, and finally we have Associate Professor Jonas Örtegren here locally in the room from Sweden University. So the grading committee is assembled by people that are all well acquainted what is in research or in natural science and having a deep knowledge what is required for receiving a doctoral position or doctoral degree. And after this presentation, these will be the people that will decide if the defendant is passing all these requirements. So today the lecture or the schedule will be as follows. First, the opponent, Jorge Garcia, will give a short introduction, placing the thesis work into a broader context. Then Muhammad will present his thesis work with a PowerPoint for about 30 minutes. After this presentation, we'll have a short technical break for about 5 minutes, and there we'll also stop the YouTube broadcasting. After that, we will reassemble back in the Zoom meeting room, and having the opponent will discuss the thesis work together with the respondent. When the opponent is satisfied with this discussion, the word will be handed to the examination committee, and each member will ask a few questions each. When the opponent and the grading committee feel that they don't have any more questions they to ask, we will have a short break, and we'll have a meeting together with me, the grading committee, and the opponent will meeting in a different room and have discussions for about 20-30 minutes. And then you are encouraged to stay in the Zoom meeting room and do mingling and to chat, whatever. Please don't leave this room, the Zoom meeting room, during that time, because then it will be more difficult to return back later on. So when we when the grading committee return back to the Zoom meeting room and deliver the final decision to the respondent. If the decision is positive, the respondent pass. We will have turn on all the cameras and have a sharing for the and raise our glass for the respondent. So it's not possible to say how long the whole procedure will take, but normally it will normally takes less than about 3 hours at least. Okay, so I'll start giving the word to the opponent, Associate Professor Jorge Garcia.
Okay, so I can start now?
Yes.
Okay, very well. Dear Professor Bertilsson and Professor Sidén, dear respondent, Mr. Bakar, dear members of the grading committee, ladies and gentlemen, first I would like to thank the chairman, Professor Ken Bertilsson, for inviting me to be here today as opponent of the thesis defense of the respondent, Muhammad Abu Bakar. I want to express it is a pleasure and honor to participate in this seminar. I've also been invited by Professor Bertilsson to provide now a short introduction on the research field of the dissertation we're about to attend, in order to put the work into context. The thesis is focused on power electronic topologies for a wide range of input and output voltage values. So the work is focused on electrical engineering and in particular in power electronics. Therefore, we need firstly to define what is power electronics. We could say that this matter can be defined as a set of techniques that apply semiconductor technologies to power applications. The main goal of power electronics is to deliver electrical energy from a power source to a power load, adapting the format in which energy is delivered by the source to the pattern required by the load. The keystone of power electronics is the power electronic converter. It is the electronic system that interfaces the power source and the power load. These converters can be classified attending to many aspects, such as the power level, the number of stages, ability to provide galvanic isolation, number of switches, and so on. But the most primary classification is attending at the nature of the electric parameters at both ends of the converter, which may be either AC or DC. The current research is focused on DC to DC converters, meaning that at both ends of the converter, the polarity of the voltage keeps unchanged. Examples of DC to DC converters can be found in electrical transportation applications. For instance, in onboard battery chargers that handle the energy from the battery pack to the DC link in the system. Also, they are very common in standalone facilities in which, for instance, a storage device is being charged from a PV module. But given the modularity of the power electronic solutions in the actual commercial applications, the converters, these kind of converters, appear in most of the multi-stage power topologies, being one of the most important power conversion types. As in every field of research, there are some hot topics currently in power electronics due to the most recent advances in the field, such as the introduction of new semiconductor and materials, for instance, wide bandgap semiconductors or new ferrites for magnetic elements. The advances in control systems, such as the development of new digital signal controllers, FPGAs, or embedded processing systems. The recent topological advances coming from the introduction of multi-level power schemes, complex magnetic circuits, and so on. The development of new power sources, loads, and storage units, for instance, novel machines, electrochemical batteries, or supercapacitors. Or the recent developments in control strategies, such as the new pulse width modulation patterns, control algorithms, mathematical transformations that allow for complex control. These advances have boosted the deployment of power electronics, allowing it to become a key enabling technology in applications such as the smart grid, the decarbonization of the electrical network, the integration of renewable generators in the power systems, or even electrical transportation. But given the demanding load profiles of the application of today, these converters are generally required to operate within a wide set of varying functional conditions. But in turn, the performance of the power conversion greatly depends on these operating characteristics. For instance, the efficiency of a converter depends on the voltage level at both the input and the output terminals, and also on the load itself. In fact, this efficiency will be, generally speaking, optimized for the nominal operating conditions, but will decrease, in some cases significantly, when these conditions are far from the nominal ones. There are interesting studies in the literature that cover wide input or wide output voltage variations, but not so many that cover simultaneously wide range variation at both ends of the converter. There are well-known topologies that can work with a wide range at one of the ends while keeping the other one relatively constant. And the general state-of-the-art solution is based on connecting in series two or more of those topologies. But this solution, even if it's mature and robust, it has some drawbacks, such as the cost and components count, size and weight, and complexity in the coordination of the control of the stages that can be considered as a challenge for the research. And in this topic is where the research of the defendant is focused, precisely on the development of power electronic topologies for wide input and output voltage range variations simultaneously in DC to DC converters. So this is the end of my brief introduction. Thank you very much for your attention, and now we hope we wait for the presentation from the defendant. Thank you very much.
Thank you, Associate Professor Garcia, for this very good introduction to the thesis work by Muhammad Abu Bakar. So now I welcome Abu Bakar here to give his presentation.
Thank you, Professor Kent, for the nice introduction, and thank you very much, Professor Garcia, for so impressive introduction of my field of research. Hello everyone. First of all, I would like to thank all of you for attending this seminar in this extraordinary situation where the whole world is under lockdown due to COVID-19 pandemic. My deep sympathies with all victims around the world. I hope life will be back to normal very soon. Today I am going to summarize my work towards the degree of PhD. Although it's a long journey of about 5 years, I try to make this presentation short, simple, and generalized. I hope you will find it interesting. This work relates to the research and development of next generation power converters. It includes analytical modeling, spice modeling, and an extensive experimental work. Let's start with some basic concept. What are power converters? Every electronic device needs a power source. It ranges from few milliwatt applications to hundreds of megawatt applications. The main purpose of a power source is to condition the input source to meet the requirement of the loading device. A power source can either be an isolated power source or a non-isolated power source. In offline applications, it is necessary to isolate load from the source. Therefore, isolated power converters are the requirement of commercial and consumer electronic industry. Depending on the control strategy, power converters can be classified as linear power converters or switch mode power converters. Switch mode power converters can further be categorized into soft switch power converters and hard switch power converters. Traditional power converters are generally designed for an optimum range of operation. Their performance degrades as the operating condition deviates from this range. Therefore, traditional power converters cannot meet the requirement of current electronic industry, where the main focus is on the stable performance and on the reduced volume. For example, in photovoltaic applications, the solar panel voltage varies from 125 volt to 550 volt. In electric vehicle application, it varies from 200 volt to 450 volts. Therefore, these applications require a converter that can maintain the performance stable over this wide range. Similarly, applications like chargers and electric drives require a converter showing stable performance over the wide range of output voltage. From this, the limitation in traditional converters can be put into two categories. First, degraded performance due to the extended range of supply voltage. Number two, degraded performance due to the extended range of output voltage. Let us investigate it further one by one. One of the possible cause for the degraded performance is the reduction of duty cycle with the increase in input voltage. Assume a full bridge converter is working at some certain operating conditions. Here, are the current and voltage waveforms at the primary winding of a typical full bridge transformer. In a switching cycle, the only useful interval is the time when power transfers from source to the load. Rest of the time is considered as freewheeling interval. In this interval, primary current merely circulates within the primary devices, just which adds extra losses. Let us assume operating condition changes and the input voltage increases. To keep the output voltage constant, it is required to decrease the effective duty cycle. This extends the length of freewheeling interval. More primary current will circulate in this period. The operation with smaller duty cycle results in loss of zero voltage switching, more conduction losses, more ringing and overshoots. This limits the range of supply voltage in traditional power converters. Similarly, for the extended range of output voltage, one available solution is the bench type adjustable power supply. Being bulky, it cannot get attention in this space conscious world. The other commonly used solution is the LLC power converter. Although it meets the requirement to some extent, however, there are few drawbacks, like a wide swing of switching frequency to get wide range of output voltage. Their performance also degrades when the switching frequency deviates from the resonant frequency. Not so much work has been done to extend both ranges together. the focus of power engineer has been to extend either the supply voltage or the output voltage. In literature, wherever the extended range of supply voltage has been discussed, the output voltage has been kept constant. Similarly, in the proposal where the extended range of output voltage has been discussed, the supply voltage has been kept constant. To extend both ranges together is the title of this thesis, Wide Range Isolated Power Converters. Here is the concept. It starts with an idea to split a single traditional bulky transformer into number of small transformers. In addition to other advantages like reduced contribution of total weight of transformer in a converter, this idea also provides possibility to connect these transformers either all in series or in a combination of series or parallel connections. Like with this configuration, the voltage on each transformer divides either by a factor 4 or by 2. This feature varies the effective turn ratio of the converter, which consequently differs the operational duty accordingly in both modes. These characteristics of the proposal can be used to extend the supply range of power converters by keeping the performance stable. Similarly, the provision of more than one transformer also provides the possibility to extend the range of output voltage. After rectification, all 4 transformers can be arranged to connect either all in parallel, all in series or in a combination of series parallel connections. In this way, the output voltage can be raised to 4 times the base voltage. So, then the range can further be extended in between this range. System is hanging. Sorry for the slow system. So, combining all these ideas together makes the final proposal as one size fits all solution. It extends the range of supply voltage utilizing 2 possible configurations on the input side, and it extends the output range utilizing 3 possible configurations on the output side. So, together this can raise the gain to 4 or 8. There are 4 main sections. There are 4 main design phases in this whole concept. One is to split main transformer into number of transformers. Second is controlling the primary side interconnections of transformers to get extended range of supply voltage. Third, preparing electrically isolated rectified blocks of each transformers. and fourth is arranging these isolated blocks to get extended range of the output voltage. During this work, each design is first thoroughly verified by performing analytical and experimental investigations. Finally, all designs have been combined into a single entity to make it a wide range isolated power converter. Then the full converter is applied in an example application to verify its functionality. I will briefly discuss main contribution of each design phase towards the achievement of final goal, followed by the discussion regarding the experimental investigation on the full converter. In the first design phase, the idea to split the traditional bulky transformer into several transformers has been presented. For example, a typical single transformer in a full bridge converter is transformed into n number of transformers. Here the primary windings of transformers have been connected in series and secondary windings have been connected in parallel. In this way, the applied voltage stress on each transformer will be reduced by number of transformers. And similarly, the load current is shared by the n transformers. Sorry for the interruption, there is something wrong with the connection. It's hard. Yeah.
Take a few minutes break just to check.
Sorry. An analytical comparison has been made to investigate the performance between the design of an example application with the traditional approach of a single transformer and by splitting it into 2 transformers and 4 transformers. The specification of the example characterization is set as the supply voltage for up to 400 volt, the output voltage equal to 48 volt DC and the load power of 2.2 kilowatt. So, in comparison, at load power of 2.2 kilowatt, the voltage stress on each transformer in the proposed concept is 75% less as compared to the traditional approach. Similarly, the current stress on secondary elements such as windings, rectifiers and filtering elements will also be less in the proposed design, which cuts the required power ratings of these elements and ultimately reduces the cost. The less amount of copper in the proposed design significantly reduces the overall copper losses in the proposed design. Design by splitting this transformer into 4 cuts the overall contribution of transformer's weight by 45%. For the verification of the concept, a module of having all 4 transformers and complete secondary part has been built. The reduced requirement of copper with the proposed idea provides the opportunity to make a hybrid transformer. Here the secondary windings have been made using traces of the printed circuit board, and the primary winding is directly wound on the center leg of each transformer by using Lund's wire. The model was successfully characterized at the load power of 2.2 kilowatt. The availability of several transformers provide the provision to switch their interconnections. It could either be all in series or in a combination of series parallel connections. For example, mode 1 connects transformer series connection of transformers T1, T2 and T3, T4 into parallel. This divides the input voltage on stress on each transformer by 2. In that case, the gain of the converter can be calculated by using this relationship. In mode 2, it configures all 4 transformers in series. This divides the input voltage on each transformer by factor 4, and the gain of the converter is half in that case as compared to the previous one. By considering all secondary windings connected parallel and plotting the gain against the duty cycle separately for both modes, we can see the gain of the converter is twice in mode 1 as compared to the gain in mode 2. By using the gain switch over characteristics of the proposed concept, the required duty cycle would also be high as compared to the traditional converter. For example, in that case, this is 30% high at the maximum level of the input voltage as compared to the conventional power converter. Higher operational duty cycle cuts the length of freewheeling interval, which ultimately shortens the length of the flow of circulating current. In this way, the range of the supply voltage has been extended by maintaining the performance stable. Similar to the extended range of supply voltage, the provision of several transformers makes the possibility to extend the range of output voltage. One way to achieve this is that if the secondary windings of all 4 transformers could be made electrically isolated from each other, this can be achieved by performing rectification of each transformer's secondary voltage in such a way that it could generate electrically isolated block of each transformer. Once we get isolated blocks, it can be arranged either all in series, in parallel or in a combination of series parallel connections. In this proposal, this arrangement has been accomplished by adding active switches along with appropriate control. For example, switches S1, S7 and S4 arrange the connection in series. Finally, all sections have been combined to make it a stand-alone wide input, wide output power converter. As discussed, there are 2 modes on the input side and 3 modes on the output side. it makes it 2/3 mode power converter. In the next slide, I will briefly discuss the control and working of the converter. In order to control the interconnection of transformers, an additional leg 2 has been introduced. In mode 2, this leg remains neutral, and the converter operates similar to the traditional full bridge converter. In mode 1, all three legs become active. The both outer legs acts in phase. One switch from each leg alternately participate in the transfer of power in alternate half cycles. Primary current in this mode follows two paths. For example, in one half cycle, switches S1, transformer T1, transformer T2, and then to the ground through switch SD. In the others, similarly, the other path is the device through SE, transformer T4, T3, and then to the ground. On the output side, the desired set of switches can be made active regardless of the mode status of the primary side. In this example explanation, all the output blocks have been connected as parallel, that is mode 3. In that case, 6 switches take part to make this arrangement. The 3 switches shown in red makes the arrangement to connect all positive terminals in parallel. The other 3 switches shown in blue makes arrangement to connect all negative terminals in parallel. To achieve other levels of the output voltage, the other respective group of switches can be made active. The reconfigurable structure allows to adjust the gain to address wide range of applications. By considering unity gain for the case when the primary section of the converter is in mode 2 and secondary section is in mode 3, the gain can be raised to 8 by reconfiguring the converter to mode 1 on the primary side and to mode 5 on the secondary side. All concepts given in this proposal have been verified by performing an extensive experimental work. A compact module containing all circuit elements along with the separate control card has been developed. Then both cards have been connected by using a plug-in type connector. A PC based user interface has been built to switch the converter between different functionalities in order to verify the full concept. The module is characterized for both the wide range of supply voltage and the output voltage up to the load power of 1 kilowatt. As said, mode 1 and mode 3 together can be used to extend the supply voltage. Here is the demonstration. Assume a typical converter is running at some instant at the input voltage of 200 volt with effective duty cycle say 90%. At some point the operating conditions changes and the input voltage rises to 400 volt. To maintain the regulation, the effective duty cycle needs to be decreased, which extends the length of freewheeling interval. In the proposed design, instead of decreasing the duty cycle, it switches the converter from high gain to low gain mode, thereby sets the operational duty cycle high again. As seen, the operational duty cycle is in both cases is the same despite the 100% change in the supply voltage. The comparison between analytical and experimental analysis shows similar characteristics. These are the performance curves drawn separately for both input modes, that is mode 1 and mode 2, by keeping the output mode constant, which is mode 3 in that case. The experimental curves have been drawn at the maximum level of the input voltage for each case, that is 200 volt and 400 volt. The performance of the converter has also been investigated over the full supply range. As seen, it keeps the performance stable. It can be explained as from 100 to 200 volt converter operates in mode 1, efficiency decreases due to the increase in input voltage. As the supply voltage crosses 200 volt, the converter switches to mode 2, resets the duty cycle high again and makes the performance stable. Similarly, the performance of the output section of the converter has also been investigated for all possible solutions. It also shows good performance. In the first case, input section is set to mode 1 and the efficiency is recorded by switching the converter from mode 3 to mode 5. In the second case, input mode is switched to mode 2 and the same procedure is repeated. Similarly, converter also shows a stable performance over the full range of output voltage. There are few considerations in this design. Since there are more than one transformers, the air gap should be similar in each transformers. The other consideration is the switchover of modes. The switches will become active from off state to on state or from on state to off state. So, the maximum inrush current needs to be addressed. So, the other thing is the placement of output control switches. When converter changes the mode, the effective parameter of the converter will also differ. So, it also needs to be considered during the design phase. Before concluding this work, I would like to present a short description of my previous work that I have already been presented in my licentiate work. It was about the construction of controlled leakage inductance transformer. As we know, leakage inductance plays a wide role in achieving the soft switching. Usually, it is not sufficient to keep the converter soft switch over a wide range. So, it is necessary to increase the output leakage inductance. One way is to connect an inductor in series with the main transformers. This reduces the power intensity. So, we try to fix it inside the transformers. For this, I place the spacer in between primary and secondary windings. Then the ferritroids have been inserted to control the leakage inductance. We characterize this transformer up to the load power of 500 watt. Then we realize that it becomes less efficient, and there are the losses which cannot be overcome in this, because these losses are inside the transformer. Then it is difficult to manage. Then we switch to the other concept. As a concluding remarks, I would say the proposed concept has been successfully demonstrated in an example application of a power converter. It demonstrates stable performance over a wide range of supply voltage and output voltage. The proposed concept enables the operation with high duty cycle, minimizes conduction losses, ringing, overshoots, and improves electromagnetic interference characteristics. The flexible reconfigurable structure that has been developed simplifies the implementation of power converter in a wide scope of applications. The use of multiple transformers further facilitates heat management and reduces overall transformer weight. The parallel connection reduces the power rating of secondary elements, which further cuts the cost and improves the power density. Although the concept shows satisfactory results, an intelligent control strategy is required before implementing it in a commercial applications. As a part of future work, an adaptive control strategy has been planned to make it commercial. After that, the approach will be extended in a bidirectional application. Additional investigation on how the gain of the converter can further be extended could also be a part of future work. Before finishing, I want to acknowledge everyone for their direct and indirect support towards my success. First of all, I would like to express my deep, sincere and gratitude to my professor Kent Bertilsson for his continuous support. I always found you waiting for the fruitful discussion. I learned a lot from you. Thank you. My co-professor Johan Sidén, for your occasional support. Professor Bent Oleman for providing such a valuable feedback on my thesis. My lab fellows for creating such a valuable environment in the lab. Administrative staff, without their back-end support, it could have not been possible. Technology and IT personnels, without whose support made this examination possible. Finally, my family, my friends, my colleagues, who have always been supporting and encouraging me. Thank you very much.
Thank you very much. Okay, then we have a short technical break here for 5 minutes. So, well, we take 8 minutes, so we are 10:30 sharp. Okay, thank you very much.